So our next speaker is Cornelia from Iowa. She will talk about a Faraday study of nonthermal filaments.
Okay, thanks so much. We've heard an amazing suite of talks, both about the magnetic field and the interstellar medium throughout the sort of galaxy at large. And I'm going to focus on features that trace the magnetic field in the very center of the Milky Way. I think Alyssa yesterday in her cartoon of the galaxy called this region special. That was very generous. I think what she probably meant was it was pretty messy, or maybe in Carl's words, nonconformist. So the image in the back of this first slide is an image that's been around for a few decades now. It's a low-frequency view of the Galactic Center, and one of the most prominent features in this image are these very linear filamentary structures that are one of the ways that we trace the magnetic field in this region. I have a lot of collaborators on this project, and my students at University of Iowa are listed in yellow. So to just give a little background to set the stage for what's going on in the Galactic Center, the last 2 decades have brought us a more thorough understanding about the energetics in this region. And I would say in large part, the energy is dominated by massive star formation. And so in the bottom picture, you see the central molecular zone. So this is a few hundred parsecs at the very center of the galaxy. The red is tracing dust associated with molecular clouds, some of which are very dense and in a few cases about to form something like a massive cluster. The green and blue represent recent and past star formation that has left a huge impact on the interstellar medium. So in the top panel, you have a zoomed-in view of the near-infrared, far-infrared, and X-ray. You can see the locations of some of the very prominent massive clusters. And again, you can see the imprint that they've left on the interstellar medium. Now, I mention this because we think on larger scales, there is likely to be a galactic wind, and this wind may in large part be fueled by these massive star activities. The wind may also have a magnetized component, and on large scales we do see evidence for vertical magnetized structures rising out of the plane of the galaxy. What we're going to focus on here is what are the ways that we can probe the magnetic field on smaller scales, and presumably that magnetic field on smaller scales is connected on larger scales to these outflows. But we do have to be very careful when we think about things like that. So the 2 main ways that we use to study the magnetic field in this region are, one, by using these non-thermal filaments essentially as direct probes of the magnetic field in this region. These are synchrotron filaments, so they're similar to the filaments that we just heard about. They tend to be quite extensive, and they can be very, very, very narrow. You'll see some images coming up showing just how extreme these filaments are in their dimensions. They have spectral indices that are consistent with being non-thermal. When you correct for the effects of Faraday rotation, in all cases you can actually see that the magnetic field lines up along the length of these filaments. And so these vectors here are representing the corrected magnetic field vectors. These filaments are strongly linearly polarized, in some cases upwards of 60%. So they can be quite, the bright ones can be quite easy to see with radio interferometers. The field strengths can be estimated through a variety of ways in the Galactic Center. I think we're settling on overall magnetic fields in the filaments being closer to 100 microgauss, up to, in some cases, a milligauss, and then in the ambient region around the filaments, which we also think is magnetized, the field strength may be lower. Now, at the same time, we have magnetic fields in the clouds. And I'm not going to say much about this other than to just show that there has been some very high resolution work done by Giles Novak and others showing that the magnetic field in the clouds that intersect, at least in projection, the non-thermal filaments is in a completely opposite orientation. So again, these are magnetic field vectors as traced in a number of dense clouds. There's also some indication of absorption filaments, which are more aligned with with different field directions. So here's HCO plus in absorption, those dark filaments. This is within a dense cloud that's actually quite compact. And when you study the magnetic field as traced by dust polarization in that cloud, you see strong alignment along the cloud and in line with these absorption filaments. So one of the outstanding questions is, what is the relationship between the field in the clouds in the galactic center and then these larger scale vertical filaments? So there are a whole bunch of outstanding questions related to the origin and the nature of these non-thermal filaments in the galactic center. We have yet to really nail down carefully the energetics, the spectral index, the particle aging, the magnetic field strengths. We're very interested in the physical connection of the non-thermal filaments in many cases to both regions of molecular and ionized gas. The view toward the galactic center can give us insight into the intervening medium. You can also, once you correct for that, you can learn about the field in the filaments, but there, as we know, there are many components toward the galactic center which will contribute to very, very large rotation measures toward this region. And then ultimately, we want to understand the connection to these larger scale features in the galactic center. Now, the brightest and most prominent region of filaments in the galactic center is the radio arc. And the previous work on the radio arc is actually now, gosh, many decades old. And so in terms of, they're very high resolution total intensity maps, but in terms of really understanding the polarization and the magnetic field orientation in this bundle of filaments, there hasn't been much work done since the early work of Farhad Yousefzadeh and Mark Morris, when they had a very small bandwidth at the VLA to work with and no ability to do spectropolarimetry. And so that has really changed in the last decade or so. The Australia Telescope Compact Array has been doing this for a long time, and the VLA recently, with its upgrade, is for the first time able to do spectropolarimetry across very broad bands. And so we have designed a study to essentially go back and revisit the radio arc to try to get a handle on what is happening on very fine scales. And really this project serves as a pilot for someday being able to do the entire galactic center using the same technique. So today I'm going to talk about some preliminary results. I'm going to focus mostly on the fairly stunning VLA images that have come out of this work. I'm going to show also some polarization results. We have also covered the same fields with the Australia Telescope Compact Array just during the last year as a nice complement and also a check. I appreciated in the last talk the check with the Westerbork data, because when you start to see these filamentary structures, when you're looking at polarization in detail, it's nice to have a check that you're seeing this with two different instruments. In the case of the VLA, there's still some kinks to work out with how you mosaic wide fields of polarization and have the sensitivity to polarization, to correct for that across the primary beam. So this is one of our images in total intensity of the radio arc at very high resolution now. And for the first time at Sband, this is one of the new capabilities of the upgraded VLA. And so right away you can see extreme filamentation structure. Again, this is a combination of multi-configurations to get sharp resolution. All of these features are seen at all wavelengths. They've been seen for decades. These are presumably real striations in the non-thermal filament structure. So that's the Sband image. We also have images at slightly higher frequencies. So this is 5 gigahertz VLA. And so again, you can see now in more detail some of the striations. You can see that the brightest filaments actually usually resolve into multiple bundles of filaments. You can also see some arc-like filamentary structures that appear to cross over the non-thermal filaments. And the depolarization, the polarization maps are very interesting because you can actually see that this is presumably thermal material possibly lying in front of the filaments, because you can see depolarization channels associated with extensions of these curved arc-like features. At 10 gigahertz, we're losing some sensitivity to extended features, but again, we're seeing very narrow ability to resolve these filaments into, in some cases, less than a tenth of a parsec. So this is just a zoomed in view of the filamentary structure in the arc from our 5 gigahertz image. Just as a side note, we've discovered a very, very, very bright and interesting source. This is an incredibly compact source. We can't even resolve it at Q-band with the VLA. It's got a very steep spectrum and an unusually compact and interesting molecular cloud associated with it. So if you have any ideas on what you think it might be, we can maybe talk at lunch. So the polarization is shown here in this image. This is just one very small part of the radio arc. This scale in this image is now just a few parsecs across, and so you can see clumps of polarization, and this is how we see the polarization in the galactic center primarily, these small clumps. You can see that these are electric vectors. They haven't been rotated yet, derotated, but you can see a lot of order among the clumps, and then you can see from clump to clump that there are variations. So this already, without even doing the rotation measure study, indicates that things are changing over very small scales in this region. And again, the polarization fraction here is quite high. These are very strongly magnetized filaments. Here's another view of the polarized intensity, and what we've done here is we've done the sort of first pass at our rotation measure. So we've sort of looked at rotation angle versus lambda squared, and we get very large rotation measures, which have been known before, but rotation measures ranging from a few thousand to about 5,000 radians per meter squared. And again, these rotation measures, here is the rotation measure sampled at 3 different locations. And so the rotation measure is changing over very, very small scales. And one of the main goals of this research is to try to get a handle on whether or not this rotation is happening at the site of the filament, along the line of sight, and possibly even internally. And so it's most likely going to be a combination of all of those things. To do this in much greater detail, we will be employing the Faraday Synthesis technique, and this will be vastly improved with our Australia Telescope compact array data because we have complete coverage from 1 to 10 gigahertz as opposed to our VLA data, which is broken up into chunks. And so we'll look forward to working on that this summer. I'll just end by mentioning 2 things. We are seeing intense filamentation on small scales throughout the galactic center. These are just some snapshots of other regions of the galactic center outside of the radio arc. And as the previous speaker said, our needs are, of course, detailed observations, especially in polarization, and simulations. And I was very inspired by the work of Clark, Peak, and Putman with their rolling Hoff transform, and I'll be working on trying to quantify the numbers of these filaments in the galactic center to see if we can get a bigger picture of what the structure of the magnetic field looks like in this region. So thanks.
Do you also have time for one question? Okay. 82.
Unbelievable.
Oh wait,
filaments.
let me show. I have a. This is. I thought I'd end with
Yes,
this.
yes. Let's end on that one. I had done a VLA proposal trying to look at filaments not in the galactic center in an external galaxy, and I had worried about internal Faraday depolarization. Basically, use the best estimates for the electron density and the magnetic field in these external filaments, and at L-band, you would just wash all the polarization out. But you're clearly not doing that here. You're getting nice signals. I mean, so do all of the numbers that you get from your answers make physical sense with what you would expect in these filaments?
Well, I mean, we haven't, the large rotation measures toward the galactic center are consistent with other sources in the galactic center, and sort of just the increase in electron density and stuff along the line of sight. So we haven't, I mean, so far the rotation measure fits seem to be consistent with external Faraday rotation. We haven't, I mean, I think that's what the Faraday synthesis is going to help us disentangle, is a little bit about whether or not it's a combination of external or internal or just purely external. It's going to be I mean, as everything goes toward the galactic center, it's going to be complicated. I think we're most interested in the change of the rotation measure along the galactic center. A lot of people have looked toward the galactic center with point sources and other objects, but people haven't had sort of 50 parsec lengths over which to probe the rotation measure. So.
So, Cornelia, can you say anything about what's occurring here? Are the gas following the field, or is the field determining where the gas is?
It's sort of a chicken and egg question, right? So do you mean on large scales, Ed, or?
Well, along these filaments, for example.
Well, the filaments, I mean, the filaments are tracing, so there isn't really any gas other than the relativistic electrons along the filaments. Yeah. So but it is clear that there's some indications where these non-thermal filaments intersect ionized and molecular clouds, there may be some interactions occurring.
Okay, so thanks, Cornelia.